In this video, we're going to do another work calculation. However, it's going to be made more interesting by the shape of the container. So what we have here is a parabola, y equals x squared. It's being rotated around the y-axis and then filled with water. So let's start with a 2D diagram here. We have x and y, and we have y equals x squared. And so we're going to spin this around the y-axis. And we can imagine that, as a quick sketch, as this kind of parabola. And the final point here is at y equals 3. That implicitly means that we've started down here at the bottom at y equals 0, just to match with the y equals x squared parabola starts at y equals 0. Now what we're going to do is actually have a pipe a little higher than that. So we're actually going to move this down a hair. Here we go. And recognize that the shape goes a bit higher, up to y equals 4. And there's a pipe outlet there. So that's at y equals 4. But the actual water that we start with is only down here at the bottom. Well, once again, the lift distance is variable. So if we imagine trying to lift this water out of the tank, the water at the top, we only have to lift it 1 meter. The water at the bottom, we have to lift it 4 meters. The water in the middle, it's a different amount of meters. So that tells us that we need to break our problem down so we can work with our force times distance. And again, we're going to take our approach from previous examples. We're going to take circular slabs that are, guess what, delta y thick. So we're going to consider slabs of water, delta y thick, and at height y. So imagine a generic slice here, that's y height from the bottom, delta y thick. We'll do a side diagram here to make that a bit more clear. Maybe just focus on this side of the tank. So here's 4. Here's our slab, delta y and height y. We can then study the work to lift the slab. Well, the work is always force times distance. Now the distance, in this case here, if we're taking a slab that's y away from the bottom, and we're lifting it to a height of 4, we have that nice little diagram that tells us we have the remainder of the height to go, so the distance will be 4 minus y. And the force is going to be easier if we think of it broken down into mass of what we're lifting times the acceleration that it's being subjected to through gravity. So we're going to do one of these little tree diagrams again. The mass is broken down to the volume and the density. And the acceleration is just g, the acceleration due to gravity. And then our lift distance is still 4 minus y. So I'll try to be careful with my g's and y's here to make sure they aren't getting confused. Now the density we know, that's the density of water. The tricky part here is going to be the volume of the slab. So this is going to be a little more involved because of the more complicated shape of our container. So let's take a look at it on the next page. We're looking at the volume of the slab, and it's going to be based on rotating this parabola here around the center. So what we get is a circular shape that is delta y thick. And if it's circular, what we really would like to know is the radius. So the volume of this circular slab is going to be pi r squared area times the thickness. That'll give us a volume. And again, it's not quite a perfect cylinder, but the smaller delta y gets, the more accurate this gets. And when we do an integral, our delta y's are going to 0 anyway, so this is a perfectly good approach for finding the volume. The challenge then is finding the r. However, the r is actually the x on the parabola, y equals x squared. So if we want to know what our radius is, it's the same thing as the x-coordinate on our slice. And the x-coordinate on our slice, we just turn this around, is equal to the square root of y. Similar to our volume calculations with volumes of revolution, we're using the same kind of construction here as well. So the volume that we're looking for is pi times our radius squared times delta y. So our volume is in terms of our formula with y's is pi square root of y all squared delta y. And that actually turns out quite nicely. The square root and square cancel. We end up with pi times y times delta y. Perfect. Going back a slide for a moment, here's the decomposition we had for the work to lift one slab. We now have a missing ingredient for our volume determined, and then we just need density g and 4 minus y. So the work to lift one slab is going to be equal to our volume, pi y delta y, times the, I already forgot, density, gravity, 4 minus y. Density is 1,000 kilograms per cubic meter. G is the acceleration due to gravity, and 4 minus y is the lift height. We're just going to tidy that up, bringing the delta y to the end, and bringing all the constants to the front. So we're going to have pi, and 1,000, and a g, times a y we haven't got yet, and a 4 minus y. And I'll try to again make those y's as distinct as possible from the g's, and delta y at the end. The beautiful thing about calculus at this stage, now that we've done this hard analysis, is that the next step to get the total work simply involves taking the work for each slab and adding it up with an integral. So we can literally copy everything down here, g, and our y, 4 minus y, and dy instead of delta y, but that's the only change there. And then we think back to the scenario we were given. We were told that this was filled with water up to the level y equals 3. So if we think of the slabs that we're going to take, there's going to be a slab at y equals 0, there's going to be a slab at 0.5, 1, 2, 3, 4, but our last slab that we're going to lift is going to be at y equals 3. So we're going to have y equals 0 and y equals 3 as the limits of integration. Now that distinction between the slabs that we're lifting and the end height, things like that, can be confusing because they're all interrelated and it's not necessarily clear at the first glance. Again, what I like to do is think about the scenarios. At the y equals 3 limit, what is actually happening? Well, we're going to lift by 4 minus 3, which is 1 meter. Does that make sense in our scenario? Absolutely. The last piece of water that we're going to lift is going to be lifted 1 meter. There is no water that we're lifting just a half meter or 0. That's not part of the scenario. The last slab is at y equals 3. The lift height works out to 1 meter. That's exactly what we would expect from this calculation. And that's it. We've set up our integral, and we'll leave it to you as an exercise to compute the actual value of this. Again, this is a straightforward integral. The only thing that you might want to do first is expand this into separate terms so that it becomes very straightforward to integrate. Add 1 to the power, divide by the new power, and multiply by some constants.